section, we are going to talk about something called the cross product. And the cross product is related to torque. And that leads us kind of into this idea of angular momentum, which we'll talk about a little bit later. So it turns out that there's two ways that you can multiply, and I'm using multiply sort of in air quotes, that you can multiply two vectors together. And one way that you can multiply two vectors together is through the dot product or the scalar product. And we talked about that when we defined work as the force dotted into the displacement vector. And that dot product was the magnitude of the force, the magnitude of the displacement times cosine of the angle between those two vectors. Well, it turns out that another way that you can multiply vectors together is by taking the cross product or the vector product between those two vectors. And when you take and you multiply vectors in this way, you end up getting a new vector instead of a scalar, which is why it's called a vector product. So it turns out that torque is the vector product of the distance, or the vector that represents the distance from the axis of rotation out to where the force is actually applied. So here's the axis of rotation of this disk, and then the force is actually applied here at point P, and so R is that vector that points from the axis of rotation out to the point where the force is applied. And if I take that vector R and I take the vector product or the cross product with the force that's applied, then I get something that tells me the torque. And that torque is a vector quantity, and so when I multiply the vectors in this way, I get a new vector. So we're going to talk a little bit and define what the cross product is and what the vector product is, just in general terms, and then we can come back and talk about this a little bit later. One thing that I do want to point out is that the direction of the torque, in this case the vector product of these two vectors R and F, is perpendicular to the plane that's containing those two vectors. So my vector R is lying sort of along that disk, and the force is lying also sort of along the plane of the disk, and the torque is actually, the direction of that vector is perpendicular to both the R value and the force value. So if I'm given any two vectors, I'm going to say vectors A and vectors B, I can determine the vector product, which is A crossed into B, and it's defined as a third vector. So when you multiply the vectors according to the cross product, you get a new vector, and that new vector is perpendicular to the original two vectors. So here's my vector A that's kind of in the plane of this disk, and vector B, which is also in the plane of the disk. These don't represent physical quantities right now. They're just a mathematical representation of a vector. And there's some angle between those two vectors. And we notice that when I take the cross product between A and B, the magnitude of that cross product is just the magnitude of the first vector A, so the length of the first vector A, the length of the vector B, times sine of the angle between the two vectors. And the direction of that cross product between those two vectors is a new vector which is perpendicular to the plane containing the original two vectors. Now, there's two directions that are perpendicular to the plane. One direction is upward and the other direction is downward. So how do we decide which is the correct way to determine what the direction of that cross product is? And it turns out one way we can do that is we can use this thing called the right-hand rule. And the way the right-hand rule works is you take your fingers of your right hand and you put them in the direction of vector A, and you then curl your fingers towards the other vector B, and then the direction that your thumb points is the direction of the cross product between those two vectors. So if I imagine taking my hand, fingers along here, curling my right hand fingers this way, my thumb would point upward. But it has to always be perpendicular to the plane containing the original two vectors. Well, it turns out the vector product is not commutative. In other words, the order that you multiply the vectors according to the vector product does matter. So if you take A cross B, it's exactly the negative of it taking B cross A. And you could actually use your right hand and imagine going, starting with vector B and crossing it into vector A, and your hand would have to be reversed in order for that to happen. So it would give you exactly the opposite direction. If A is parallel to B, meaning that the angle between them is either 0 or 180 degrees, then it turns out that A cross B is equal to 0. And the reason for that, I'm going to go back a slide for a second. The reason for that is because the magnitude of the cross product is the magnitude of each of the vectors times sine of the angle between them. And so if the angle between them, if they're parallel and the angle is 0, sine of 0 is 0. If the angle is 180 degrees, if they're anti-parallel, going in opposite directions from one another, sine of 180 is also 0. So any two vectors that are parallel to one another, the cross product is going to give you a 0 value, which means if you take A and you cross it into itself, you get 0. On the other hand, if you take A and it's perpendicular to B, then that means that the angle is 90 degrees. And so the magnitude of A cross B, that new vector, would just be the magnitude of A, the magnitude of B times sine of 90. Well, sine of 90 degrees is just 1, so the cross product magnitude of these two vectors is just the magnitude of each of the vectors multiplied together. So this is exactly opposite to the dot product. For the dot product, if the two vectors were parallel to one another, we have the maximum value for the dot product because cosine of 0 is 1. And if they were perpendicular to one another, then the dot product was 0. And if you think about it in terms of work, any force that's perpendicular to the displacement does not contribute to doing any work on the system. So in terms of unit vectors, we can think about how we would take the cross product between two unit vectors. And so if I take the cross product between any two unit vectors that are alike, like I crossed into I, or J crossed into J, or K crossed into K, it's always going to give me a 0 value because the angle between these is always going to be 0. On the other hand, if I take the cross product between two unit vectors that are not alike, they represent unit vectors along each of the different coordinate directions. So the I is representing the x direction, J is representing the y direction. So the angle between two different unit vectors is always 90 degrees. So a unit vector has a length of 1, so it's always going to be 1 times whatever direction that cross product gives us. And so it turns out if you go in a cyclic order, like I to J, which is the order like X, Y, Z, I crossed into J gives you a new vector along the Z direction or the K direction. If you go again cyclically like Y, Z, so J crossed into K, that gives us a directional vector that's in the X direction, the I direction. And then if you do K crossed into I, again, each of them has a length of 1 and they're at 90 degrees. So that gives you a unit vector along the Y direction. So like Z crossed into the X direction gives you the Y direction. You'll also notice that there's a minus sign in front of these other quantities because if we reverse the direction of the cross product, we know that, that there has to be a negative sign in there. So the signs are kind of interchangeable in terms of where you put them. So for example, if I take I and I cross it into negative J, that minus sign can actually be brought out front, and it's the same thing as negative I cross J, which is just I crossed into J, X crossed into the Y direction gives you the K direction, but then there was a minus sign out front. So the vector products are important in physics in a lot of different ways. We're not going to use it a lot right now, but it's important to introduce this concept because it is related to torque, and we'll come back and talk about that a little bit later. So in general, we would probably have two vectors that we would maybe want to multiply according to the cross product. And if we were to do that, we would want to write out each of the vectors in terms of each of their components, their X, Y, and Z component for A and B. And then we can multiply these together according to the cross product. Now this here is actually a matrix, and it's a way of multiplying vectors, which is a little bit hard to explain right now unless you understand vectors. But essentially, if I were to just multiply these together and I would FOIL it out, like take AXI, and I would multiply by BXI in terms of the cross product, the I crossed into the I would give me a 0. But if I took AXI and I multiplied it by BYJ in terms of the cross product, I'd have an AX, a BY, and then an I crossed into a J gives me a K. So if I come down here, that's that first term, AX, BY in the K direction, and I would just have to FOIL it out for each one of those particular terms. So I'd have like basically 9 terms, but 3 of the terms would cancel out. So let's look at an example where we just actually FOIL it out. Example, we have a force that has 2 units of force along the x direction and 3 units of force along the y direction. It's applied to a rigid object that's pivoted about a fixed axis aligned along the z-axis. So basically you could think about it as that previous picture with the disk. And so we know the force is acting sort of along this direction. The force is applied at a point that's located at a distance of 4 meters along the x direction and 5 meters along the y direction relative to that central axis. And we want to find the torque that's applied to this object. So we know the torque is the cross product of this position vector with the force vector. So I can plug in the value for my position vector, 4 meters along the x direction and 5 meters along the y direction. And I want to cross it with the force, which is 2 newtons along the x direction and 3 newtons along the y direction. So what I'm going to do is I'm going to actually FOIL this out. So I'm going to multiply the 4 times the 2, the 4 times the 3, and I'm going to keep the unit vectors in the expression and make sure that I take the cross product between them. So if I write them all out and I do this FOIL, I would have 4i crossed into 2i. That's the first term. So 4 times 2, and then I crossed into I. And then I would have 4 times 3, and then I crossed into j. So 4 times 3, I crossed into j. And then I would FOIL the 5. So 5 times 2, j crossed into I. So 5 times 2, j crossed into I. And then 5 times 3, j crossed into j. So j crossed into j. That's missing a unit vector. So as I look at this, I realize that 2 of these terms are going to be 0 because I have a unit vector that's crossed into itself, like I crossed into I and j crossed into j. So both of those terms are going to be 0. So I have 2 terms left, and so I have 4 times 3, which is 12, and then I crossed into j, and I crossed into a j gives me the k direction or the z direction. And then I have 5 times 2, and then I have j crossed into I. That's opposite of ij, so that's going to give me a unit vector that's in the negative z direction or the negative k direction. So there's the 12 in the k direction and the 10 in the negative k direction. And so then when I add those two together, taking into account direction, 12 basically plus a negative 10 is going to give me 2. So the total net torque on this system is 2 Newton meters, and it's acting along the z direction or the k direction.